Hello, my name is Alyssa Studebaker and I work as the Business Specialist for Moldex 3D, and I'm going to be taking us through today's webinar. So first, let me begin by explaining exactly how Moldex 3D can benefit your company. First, Moldex 3D can make your company more competitive by reducing development time through fast and accurate analyses. You can use the software to spot potential problems and create solutions before actually cutting the mold. Also, your company will be able to optimize process conditions that will reduce cycle time and energy consumption while improving part quality. Second, Moldex 3D software analysis will reveal visual defects like weld lines or sink marks, as well as detect underlying causes for dimensional instability in the cavity. And lastly, with these tools you will be able to reduce your lead time and achieve lean production, which of course would improve your efficiency. Now let's talk about the private cloud. What makes the Moldex 3D private cloud an advantageous option? Well, first, the price. It comes at a low cost in which you are only paying for the usage of the product. When it sits idle, you are not paying anything. Overall, this reduces the price that you pay per analysis. Next, the licensing. We allow up to 4 users to use the software simultaneously. That means if one company buys one license, they can have 4 employees working on the cloud at the same time from different computers. As far as the capability, our software simulates flow, cool, pack, warp analyses, as well as multi-component molding. And lastly, the hardware. The private cloud allows you to take advantage of good hardware by allowing you to use a lower-level computer system to connect with a high-level computer system and run an analysis. So, for example, if you're at home with your laptop and you want to run an analysis on your computer at work, you don't have to run all the way back to the office to do that. You can use the cloud to connect your laptop to your work computer and conveniently run a high-level analysis from home. Now let's look at what the Moldex 3D cloud system includes. There are pre- and post-processors, flow, pack, cool, warp analyses, and parallel computing, which allows you to use more than one CPU to run an analysis. The benefit of that being that it would greatly reduce the analysis time, because it uses the power of a cluster of computers instead of just one. There's also solution add-ons, which include multi-component molding, fiber orientation analysis, and the I2 analysis. This allows you to output the simulation data into FEA software like Ansys and Abacus so that you can run FEA analyses from there. And finally, the private cloud includes the eDesign Sync system. These are basically plug-in systems inside NX, ProE, and SolidWorks from which you can export a mold directly from these CAD systems into Moldex 3D and run your analysis. Moving on, this slide demonstrates the advantages of parallel processing. Now, with parallel processing, the time needed to run an analysis can be substantially reduced. For example, for a desktop computer with a 4-core i7 CPU, the flow pack analyses of a model with 1 million elements can typically be finished in just 1 hour, and the cool warp analyses can be finished in half that time. Now you might be wondering, how is this possible? Well, because with the parallel processing performer, you are able to attach more than one core to run an analysis and significantly reduce the amount of time needed to obtain the analysis results based on the number of cores that are added. That's demonstrated by this graph right here. So you could see that with only one core, it takes a lot more time to run an analysis than it would with, say, 8 cores. And the more cores you add, the faster it becomes. Moving on, this is the way the private cloud and the pay-per-use system works. First, users prepare pre-processing data on the client-end computer, and next they will submit the analysis jobs to a workstation. The workstation then auto-runs Moldex 3D analysis, And when that's finished, users will be able to download the post-process results back onto the client computer and review the results to look for ways to optimize their design. Next, the Moldex 3D flow analysis. Moldex 3D is able to predict the melt front, weld lines, air traps, short shots, and all kinds of other problems that can occur during the filling analysis. This also includes unbalanced filling and thermodegradation of the plastic. With this feature, you can save time and money by catching potential problems before the parts are manufactured. Here you can see the flow analysis running. You can see the weld lines predicted by the software in this picture below. During the packing phase, Moldex 3D can simulate the density variation and melt flow due to material compressibility. On the right side is an animation of the slicing function, which cuts a plane through the model. And this allows you to see what is occurring on that plane throughout the model. And you can also see the volumetric shrinkage, which is the percentage that the plastic has shrunk during the packing phase. And the animation is able to show an isosurface display, which shows the solid elements that correspond to a specific value. And we usually use this to find areas of high volumetric shrinkage. And those are areas that tend to correlate with areas that are prone to either voids or sink marks. Moving on to the cooling analysis, this simulates the mold temperature, cooling, efficiency, hot spots, and cooling time. Below we see two pictures and an animation, and each of these is the same model. The first one shows the cooling temperature inside the cavity. This is the temperature that the cavity has reached at the end of cooling. It can be used to find hot spots inside the plastic. The second picture depicts the cooling efficiency, and this shows the amount of heat each individual cooling line will use. With this tool you can detect inefficient cooling lines that can be removed. This will save you money with the tooling cost later on. And this simulates the part warpage due to volumetric shrinkage and further helps to control these defects before the mold is built. These animations will essentially show you how the part will warp. Moving on to the fiber analysis, this is an add-on solution that simulates the 3D fiber orientation that calculates the process-induced anisotropic properties. And the animation shows the slicing function that cuts through the part. You're able to see in detail the various directions of the fiber inside by looking at this picture here. And on the left-hand corner you can see a close-up of the fiber. That's this right here. And it shows both the concentration and direction of the fiber in that area. With this tool on this slide, you will be able to simulate part inserts, mold inserts, and two-shot molding, also known as overmolding. Here, we see both the flow simulation of the plastic part over a part insert, as well as the warpage that will result from this flow. Next is the Moldex 3D viscoelasticity, and this tool predicts the flow-induced residual stress and prevents the potential design problems. In the pictures below, we can see the predicted residual stress calculated by our solver over here, and the actual residual stress as observed by chemical tests. Moldex 3D can also precisely predict the birefringence caused by complicated process-induced anisotropy in the cavity. In the pictures below, we can see the predicted birefringence as determined by our solver, and over here the actual birefringence as determined by an experiment. Now, our I2 interface, or FAE interface, is a series of interface modules to integrate Moldex 3D and structural CAE software like Abacus, Ansys, etc. With this, you will be able to export fiber orientation data into these structural CAE softwares and test that model with various loads as well as natural frequencies of whatever the structural analyses offer. And below we can see the comparison of a part that is fiber filled and one that is not. This slide talks about our extensive material database in which we have over 5,000 different materials users can view and also view the material properties. Users are also able to export materials into the user bank to modify the material data so that it will better fit their analysis. Now we will move on to some case studies. In this section, we're going to be reviewing 2 case studies in which Moldex 3D was used to improve the design of a part. First, if you look at the picture on the left, you can see one model with a hinge. It has only one gate. The nominal wall thickness is 0.08 and the thickness of the hinge is 0.025. Now because the hinge was so thin, it was hard to fill and it caused a short shot. The picture on the right side is the same model with 2 gates. By adding a gate, we were able to solve the short shot problem. Now based on Moldex 3D's prediction and the actual results, you can see that the software predicted the weld line. The weld line was a concerning defect in the part quality, being that it was a high-risk area for breakage. Now in order to remove the weld line, efficient venting was put in to remove the air trap and change the weld line location. Moving on, Moldex 3D is able to simulate multiple cavities, and based on the simulation, the software is able to provide the weight of each cavity. On the chart, you can see cavities 1 through 4 and compare the simulation part weight with the actual weight. And the simulation, as we can see, was able to give very accurate estimates. Here's an example of a company using Moldex 3D to predict warpage. After simulating the warpage tendency and volume, we added windage to compensate in the CAD model. In this case, we were able to improve the part quality by predicting the warpage and compensating for it. In this slide, you can see some base information about the model. In this case, the client in this case was primarily concerned with cooling. Now we demonstrated how conformal cooling analysis would best suit their needs. And to do this, we ran 3 tests, which you can see below. The first one, over here, was a baseline with no cooling channel or analysis. In the second, we used a baffle system. And finally, we used the conforming cooling system on the last one. Now we can see the results on this slide. We can see the part temperature distribution at the end of cooling. And we can see that the temperature of the part at the end of cooling is reduced by 10 degrees Celsius using the conformal cooling channels. Here, we can see a slice of the model base and the mold base temperature at the end of cooling. From these pictures, you can see that the conformal cooling channels are not only cooler, but also the high temperatures have been moved back into the runner system. The baffle system is still cooler than nothing, but the conformal cooling system is clearly superior. Finally, we will quickly discuss cooling time. As you can see, with the conformal cooling system, we were able to reduce the cooling time by about 1 second. Here we can see the cooling channel layout and the mesh used for this model. On this slide, we see the original design with a melt front of 80% and the original design with the Z displacement warpage. Below is a table with the warpage for the original design too with the insert. For this model, users wanted to reduce the warpage problem. The issue here was that the part was with the part insert. Because the insert is below the cavity, the warpage is non-uniform. For the first revised design, we decided that we should enlarge the gate dimensions to extend time for gate solidification and improve the packing effect. And in the second redesign, we modified the runner layout to improve flow balance and the packing effect. Here we can see that in regards to the enlarged gate dimension, there is no obvious difference between the original and revised designs. But here, although we see an improvement in the packing effect for the enlarged gate, there is still a non-uniform packing distribution in the cavity. Through this quick comparison between the revised design and the original, you can see an improvement. For this design, we adopted a 3-point model system and completely changed the runner layout. After modifying the runner layout, we found that the flow was more balanced. Thus, the non-uniform packing effect caused by the imbalanced flow can be greatly improved. Here, we see the pressure distribution inside the cavity. The packing pressure distribution here is more uniform. This finally improved on that warpage problem. Below you can see the warpage of the original design versus the revised design, and the improvements were above 50%. And here's a final comparison of all the designs, and it shows the second redesign greatly improved the warpage by providing a more balanced filling of the cavity, which provided a more uniform packing effect and uniform volume shrinkage. Now we'll go over some other success stories, beginning with the Honda dashboard. Here we can see the flow rate between the gates is unbalanced, meaning that one gate is filling the cavity a lot faster than the others. This is an indication of unbalanced flow, so we modified the gate design to improve on this and also improve the weld line locations and the packing and warping. Now in this Hyundai engine cover situation, we studied the isotropic material properties support for modal analysis to get the real natural frequency and harmonic behavior. This played an important role in that estimation. And we used the I2 interface to export the fiber orientation to ANSYS, which was then able to run a natural frequency test on the model. With this, we were able to get various natural frequencies caused by various fill times and designs. Now this company here had an issue with short shots, and while running our simulation we were able to locate the exact spot of the short shot as compared from this picture here to this picture here. And this here is a testimonial from Nissan emphasizing how user-friendly Moldex 3D is. Over here, this is a result from a simulation we did on a headlight. With this Molex car connector, the temperature difference between the top and bottom part was causing a warpage issue, which in turn caused this model to bend in. Alright, the following slides explain the level of cost saving Moldex 3D software can provide. Alright, let's look at this chart in detail. For a mid-sized company that has about 30 large molds per year and 30 small molds, each mold usually has around 6 mold trials, and for each large mold the cost is $300 per hour. For a small one, it's about $150 per hour. Now based on that previous slide, the annual cost for molds in total would be over $200,000, $216 to be exact, and that comes from mold trials and mold fix. And in the purple boxes over here, you can see a breakdown of those two large costs. Now, while we're going through this, keep in mind that this is only a rough estimation for a mid-sized company. Now, after you begin using Moldex 3D, you can reduce the mold trial for each mold from 6 to 2. For each mold, you need only 4 flow analyses and 2 full analyses. The cost to run a simulation for each mold is thus reduced to only $160. Now this slide stands in contrast to the one we saw just a minute ago, where the cost was over $200,000, and we see that is reduced to only $63,000 per year with Moldex 3D software. Again, keep in mind this is an example based on a mid-sized company, but if your company is larger or smaller, you can use the previous slides to run a savings calculation that would fit your company's size. Now here's another example. On the left side of the chart, we can see the annual cost for mold fix and revision. With Moldex 3D, that cost can be reduced by 70% or more. For label and material, the cost savings is 66%, and for annual trial and error time, that is also reduced by 66%. This brings us to our review of what the private cloud offers. The private cloud will provide users with flow, pack, cool, warp analyses, CAD interface, NX, SolidWorks, Pro-E, etc., solution add-ons like fiber orientation, multi-component molding, I2, venting analysis, etc., and parallel computing for up to 16 CPUs. We also offer up to 4 seats for any users who purchase one of the packs below. You can see we have a basic, a standard, and a premium. So, you buy 200 hours a year, and that equates to about $20 an hour that you're spending, and remember you're only paying for your usage. And you can also buy our standard pack, which is 500 hours per year. That equates to $12 per hour. Or the premium offers the best cost, only $10 an hour for 1,000 hours per year. So in conclusion, Moldex 3D helps users optimize their design to reduce cycle time, improve part quality, improve cooling design, and reduce costs. The pay-per-use model is advantageous because you only pay for the hours that you use the software.